Thank you very much for giving me the opportunity to speak, and also thank you all for being here. And yet, as we said, I'm going to talk about surfaces of general type with maximal Picard number near the Noether line. This is one of my last papers, and it is a work in collaboration with Wen Bin. And yeah, well, before I forget, yes. Ah, todavía se ve boca abajo.
Así es, así es. Es que donan.
Claro, es que no se ve la
Vale.
Ya está bien. Okay. And before I forget, I would like to say that right now I am a professor at Universidad Politécnica de Madrid. Okay, so let's begin. So the first thing that I would like to do is to write the main result of this paper that I am going to talk about. Okay, so this is the main result of our paper. And during this talk, what I'm going to do is introducing some of the concepts that appear here in the statement of this result. And well, I guess that at the end of the talk, I will sketch the proof of this theorem. Okay. And also, I would like to write down one result that was the main inspiration for this theorem. Okay. But this is not going to be the original statement of this theorem, but I'm going to write it in a language that is coherent with the notation that I'm using. Okay. But basically, what this theorem says is that okay, so to summarize, what Persson did was finding examples on the Noether line, that is the line k squared equal to 2k minus 6. And as I said, he found examples of surfaces of general type on this line that have maximal Picard number. What we did was finding surfaces with maximal Picard number in a bigger region. Okay. Actually, I have a picture for you to see how much we increase this region, if you're interested. Okay, and yeah, as I said, what I'm gonna do is talking about the main concepts that appear in the statement of these results, and then I will sketch the proof of our theorem. Okay. I will start with some things that maybe will be very easy for some of you, but I think it is good to talk about them. Okay, so first of all, let us say what are the objects that we are going to work with. Okay, we are going to work with projective, algebraic surfaces over the field of complex numbers, and we are going to impose two more things on these surfaces. The first thing we want to impose is that we want x to be minimal. This means that there are no -1 curves, because, well, if there were -1 curves, we could just contract them and we wouldn't get any singularity. And also, if we allow -1 curves, we could consider a smooth point of this surface x. We could do a blow up, and then we would get a -1 curve. So, as you can see, having -1 curves, allowing -1 curves in our surfaces is not very convenient. So we assume that our surfaces don't have -1 curves, and therefore these surfaces are minimal. We also want our surfaces to be of general type. This means that the codyro dimension of these surfaces is 2. In other words, this means that there is a pluricanonical map such that its image is a surface. Okay? And well, for those of you that are not used to work in the realm of algebraic surfaces, and you work in the realm of algebraic curves, let me say that the equivalent notion in the realm of algebraic curves is, well, this condition is equivalent to imposing the curves to have genus bigger than or equal to 2. Okay? But in the case of surfaces, this is the way we say it. Okay, we say that x is of general type, and this means that it has codyro dimension 2.
Are you assuming the surface to be smooth?
Not necessarily. Not necessarily. In some cases, we will work with smooth surfaces. In some other cases, we won't. Okay. Okay, for surfaces with these conditions, there are two main numerical invariants. Okay, so the main numerical invariants are the self-intersection of the canonical class and the holomorphic Euler characteristic. Okay, so let me talk a little bit about these numerical invariants. The self-intersection of the canonical class can be defined in a very easy way, at least if we have effective divisors in the canonical system. So if we have effective divisors in the canonical system, we can take two of them. We can count the number of intersection points, and this would be the self-intersection of the canonical class. And on the other hand, the holomorphic Euler characteristic, well, it is a common object in algebraic geometry, right? So I guess you know what this is. It is this alternated sum. Okay, but well, in this context, we have that this group, well, the dimension of this group is 1. This is known as the irregularity of the surface, and it is denoted by Q of x. and this is the geometric genus of the surface, and it is denoted by Pg of x. Okay. Why do I say that these are the main numerical invariants of this kind of surfaces? Okay, they are the main numerical invariants because if we fix them, we will get a modular space that is known as Gieseker's modular space that parameterizes canonical models of smooth minimal surfaces of general type. Okay, so actually, as I said, what this modular space parameterizes is canonical models. So we should say what a canonical model is. Okay, and the thing is that each smooth minimal surface of general type has a unique canonical model that can be realized in two ways. Okay, we can realize this canonical model algebraically. Okay, but we can also understand this canonical model in a more geometric way. Okay. So basically what we have to do is to contract okay, we have to contract the connected components of the union of the -2 curves of x. Okay, so if we start with a projective algebraic surface that is not necessarily minimal, we can get the minimal model contracting -1 curves, and then we get this minimal model that if the original surface was smooth, then the minimal model is also going to be smooth. Now, if we start from a projective algebraic surface of general type that is minimal, we can obtain a canonical model. This time, what we have to do to obtain the canonical model is contracting the -2 curves. Okay? In this case, we contract the -2 curves, and we get singularities. Okay, but the singularities that we get are not very singular. Let's say, okay, they are mild singularities. Well, let us talk a little bit more about this. Okay. Okay. So first of all, why do we contract the -2 curves of a smooth minimal projective algebraic surface? Because contracting the -1 curves, we are going to make the canonical divisor ample. Okay, so the canonical divisor of a canonical model is ample, and well, the price that we pay is that x may have some singularities. Okay, it will have what is known as dual singularities, canonical singularities, ADE singularities. Okay, so these are different names for the same thing, and these are the singularities that a canonical model may have. Okay. Now, it is important for us to speak about the exceptional divisor of the minimal resolution of these singularities that we are allowing these canonical models to have. And well, actually, we can only have 3 types of singularities, let's say. So we will have AN singularities, the exceptional divisor of the minimal resolution of these singularities looks like this. Okay, we just have a configuration of -2 curves that looks like this. Okay, and the dual graph is something like this. Okay, then these canonical models can also have dn singularities. Okay, in this case, we have a configuration of -2 curves that looks like this, and the dual graph is this linking diagram. Okay, and we also may have en singularities. Okay, so they look like this. Okay, so these are the exceptional divisors of the minimal resolution of the singularities that can appear in a canonical model. Okay, and this is going to be quite relevant for the result, as we will see pretty soon. Okay, now let us say something about some inequalities that the invariance of minimal surfaces of general type. So if we have a minimal surface of general type, then we have some conditions that the invariance of this surface must satisfy. In particular, the self-intersection of the canonical class of this surface is going to be strictly positive. The holomorphic Euler characteristic is going to be strictly positive. Then, in addition, this invariance will satisfy what is known as Noether's inequality. And they will also satisfy what is known as the Bogomolov-Millau-Kayao inequality. Okay, so these are the inequalities that the main numerical invariance of a minimal surface of general type will satisfy. And well, actually, if we have a pair of integers satisfying these inequalities, we will say that k squared and chi are, well, this is an admissible curve. Okay, so as you can see, we have already talked about many of the ingredients that we have in the statement of this main result, right? Now we know what an admissible curve is. Now we know what this modular space is. Now we know what a canonical model is. Okay, but we haven't said anything about the meaning of Picard number. Okay, so this is the next thing that we're going to do. We are going to define what the Picard number is, and then we are gonna develop some of the properties that this number has. But before that, let me just say that, well, let me say what the geographical question is. Okay, I think this is also relevant. Okay, So the original geographical question consisted in determining the admissible pairs such that okay, so we know that if we have a minimal surface of general type, then these inequalities must be satisfied. But in principle, we don't know if for every pair of invariants satisfying these inequalities, there exists any surface. Okay, so this was the original geographical question. And well, there are still some missing cases, but the general belief is that we can find surfaces for any of these invariants, for any of these pair of invariants. Okay. So since this question is kind of considered answered, there are some variants of this question that go as follows. Okay, so the variant of the original geographical question consists in determining the admissible pairs such that okay, so this variant consists in determining the admissible pairs such that there exists a surface with these invariants and it has a given special feature. Okay, this special feature can be anything. In our case, we are interested in surfaces with maximal Picard number. Okay? So if we want to summarize this paper that I am talking about in one sentence, we could say that it is a contribution to the geography of minimal surface of general type with maximal Picard number. Okay? So this would be a way to summarize in one sentence this paper. Okay? And now let us speak a little bit about Picard numbers. Okay. Okay, so in this section, we are going to assume that X is smooth. Okay. And we are going to consider the Neron-Severi group of X. Okay, the Neron-Severi group of X, at least in the context that we are working with, it can be defined as the group of divisors of X modulo numerical equivalence. Okay, and it is a finitely generated abelian group, and therefore it has a torsion part and it has a non-torsion part. Okay. The Picard number of X is precisely the rank of this finitely generated abelian group. Okay, so this is the definition of the Picard number of an algebraic surface. But actually, we are just going to need two properties of this Picard number. The first property is that if we denote by H11 this Hodge number, then it turns out that that this is an upper bound for for the Picard number of an algebraic surface. And well, actually, this Hodge number can be calculated in terms of some of the invariants that we talked about previously. Okay? So in particular, this is well, actually, let me check if this is plus q of x or minus q of x. I don't remember. Okay, it is minus 2q of x. Okay. Okay, so as I said, this Hodge number can be computed in terms of the other invariants that we talked about, and it is an upper bound for the Picard number of an algebraic surface. And the other property that we need to know is that if we have n curves on X, and we denote by M the intersection matrix of this bunch of curves. Okay, so the entry ij of this matrix is the intersection product of the curves Ci and Cj. Okay, then it turns out that the rank of this matrix is a lower bound for the Picard number of a smooth surface. Okay, so what is the conclusion of all this? If we find H11 curves on X such that the determinant of their intersection matrix is different from 0, then X has maximal Picard number. Okay, we say that a surface has maximal Picard number if it reaches the upper bound, H11, okay? So, because of these properties, if we find H11 curves on X such that the determinant of their intersection matrix is different from 0, then the surface will have maximal Picard number, okay? Another very important property is that the -2 curves of an ADE configuration, okay, are always numerically independent, and therefore they always contribute to the Picard number of an algebraic surface. Okay, so important property. Okay, so now I can explain the strategy that we are going to follow to construct surfaces of general type with maximal Picard number. Okay. Basically, what we are going to do is finding, okay, so X with maximal Picard number Okay, so we are going to obtain surfaces with maximal Picard number as minimal resolutions of canonical models that are maximally singular. What do we mean by maximally singular? Okay. Okay, so this is the way we are going to obtain surfaces with maximal Picard number. We are going to construct a very singular surface. We are going to consider the minimal resolution of this surface that actually is a canonical model, and we will get a lot of -2 curves because of the -2 curves that arise from the ADA singularities, and we will check that we have as many curves as possible, and therefore this surface will have maximal Picard number. Okay. Now, so this is the path that we are going to follow, but now we are going to talk about the main tool that we are going to use in order to construct these surfaces. This tool, let's say, or theory, is the theory of abelian covers. Okay, so if we have a finite abelian group, then a G cover or an abelian cover with group G is going to be a finite map together with a faithful action of G on X, such that F exhibits Y as the quotient of this surface by this rule. Okay. What the structure theorem for abelian covers says is that if we want to construct an abelian cover, we can start in the surface Y, and we can just consider a bunch of line bundles and divisors on Y, sorry. Okay, we just consider a bunch of line bundles and effective divisors on Y satisfying certain properties. And this will determine an abelian cover. Okay. And well, actually, this structure theorem for abelian covers was proved in general by Rita Baldini. Okay. And okay, this set of line bundles and effective divisors is known as the building data of the cover, and not only we can construct an abelian cover from this building data, but also we have information about the invariance of the surface that we get upstairs. Okay, so we are able to compute k-square of x. We are able to obtain the holomorphic Euler characteristic of x, the geometric genus, the irregularity of this surface from the building data, together with information about the invariance of y, and also we can deduce the singularities of x from the building data of this cover and from the singularities of y. Okay, so I am not gonna write down the explicit relations that these line bundles and these effective divisors must satisfy, because they are quite. I mean, they are not so easy. But I'm going to talk about some particular cases in which these relations are not that difficult. Okay? In particular, I'm going to talk about set two covers, and I'm going to talk about set two square covers. Okay? They are also known as double covers and bi-double covers, respectively. Okay, so in the case where G is just the group set2, then the building data reduces to a line bundle L and a divisor B, such that 2L equals B. Okay, so in the case of set2 covers, this is very simple. Okay, I mean, I am going to talk about a very easy example for you to have some intuitions about this theory of abelian covers. So, for instance, we can start with P2, the projective plane, okay, and we can just consider a small conic as the branch locus of this abelian cover. Okay, I didn't say anything about L so far, but actually, since the Picard group of the projective plane has no torsion, the divisor of the branch locus defines univocally a line bundle. Okay. Okay, so the line bundle will be necessarily O1. Okay. So in this case, what we get is just a quadratic. Okay. So well, this is a very easy example, but we can do something slightly different. Okay, we can start from P2, and instead of a smooth conic, we can consider two lines. Okay, we get the same line bundle, L, but in this case, the branch locus is a pair of lines. Okay, and what we'll get is just, okay, so this is a set to cover, this is a set to cover. Okay, in this case, what we get is a quadratic cone. Okay. So these are very easy examples, but there is something that, well, there are a couple things we can learn from them. The first thing is that, as you can see, this branch locus has no singularities, and therefore the double cover, the surface X that we get upstairs, doesn't have singularities. In this case, the branch locus has singularities, and a consequence of this is that the surface upstairs will have singularities. So this is one interesting thing that we see from these two easy examples. And the other thing is that the smooth conic can be deformed into the pair of lines. Okay, and in the same way, the quadric can be deformed into the quadratic cone. Okay, and this is not a coincidence. Okay, so this has to do with the theory of natural deformations, also studied in general by Rita Pardini. Okay. How did Persson find examples of surfaces of general type with maximal Picard number? Constructing set two covers with a very singular branch locus. Okay. In our case, we are going to obtain surfaces of general type with maximal Picard number, considering set two square covers branched along curves with a very particular configuration. Okay. So actually, we are interested in set two square covers. In this case, what we need is three line bundles and three divisors satisfying the following relation. Okay. And actually, let me write the formulas that we get for the invariance of the surface upstairs. Okay, so these are the formulas that we get for the invariance of the surface upstairs. Well, we don't need, I mean, for the sake of this talk, we don't need to remember these formulas, but I wanted to show you how the invariance of the surface upstairs can be derived from the invariance of the surface downstairs together with the building data of the code. Okay, so what we are going to do now is to construct set to square covers of rational surfaces and the branch locus, the divisors B1, B2, and B3 will, we will have a very particular configuration, and this is what will produce a lot of singularities. Okay, so actually, before sketching the proof of the main result, let me just talk about Hirschsprung surfaces, because actually we are going to consider set to square covers of Hirschsprung surfaces. So it will be convenient to talk about these Hirschsprung surfaces, at least to fix the notation and to show one result that is essential in order to prove the main result of our paper. Okay. Okay, so the formal definition is that, well, they are this projective bundle. Some particular cases that I am sure you know are F0, there is P1 cross P1, F1, there is the blow up of P2 at a point, okay, and so on. The rest of Hirschsprung surfaces are not so well known, maybe, but well, these two first cases are very well known. What are the properties that we have to keep in mind about Hirschsprung surfaces? Well, they are root surfaces over P1, okay, and actually they have a negative section, a section with negative self-intersection, okay, that will be denoted by delta 0, and yeah, the fibers of this fibration are isomorphic to P1, okay, and actually the Picard group of these Hirschsprung surfaces is generated by the negative section and a fiber. Okay. Now, what else do we need to know about Hirschsprung surfaces? Well, we need to know what Bin and I call Persson's trick. Okay? So this is not the official name of this result, but it will be convenient to have a name to refer to this result. Okay? And what Persson's trick says is that if we have an integer and two fibers of a Hirschsprung surface, then there exists a unique cyclic cover Okay, so this is the first part of the result, but there is something else. Okay, the other part of the result says that if we have a curve in this linear system, then it pulls back to a curve in this other linear system. Okay, and in addition to this, if we have an asingularity of a curve C at one of these two fibers, where we are, sorry, I should have said, okay, so there is a unique cyclic cover with branch locus F1 plus F2, okay? So, and the thing is that if we have an asingularity in one of these fibers, an asingularity of C at one of these fibers, and this singularity is transversal to the fiber, okay? Then the pullback of this curve will have a singularity with a bigger index. Okay, so actually this result, Persson streak, is a way to amplify the singularities of a curve. Okay, because if the singularities don't belong to the branch locus, they will be multiplied, okay, by d. And if the singularities belong to the branch locus, then the index will be bigger, and therefore we will have a more singular singularity, let's say. Okay, so we have all the ingredients to sketch the proof of the result, okay, of our main result. But actually, this result is a corollary of a more general construction. So let me write this more general theorem. Okay. Okay, so we define three integers satisfying certain relations. Then we define k squared as this number, and we define chi as this number. Okay. Then there exists a canonical model in this G-scarce moduli space, okay, where k squared is this number and chi is this number, whose minimal resolution has maximal Picard number. Okay, so yeah, as I said, this is a more general construction. And this main result is a very easy corollary from this other theorem. Okay. What these integers m and k are is not very intuitive at this point, at least. But at least let me say that k is the distance to the Noether line, Okay, K can be understood somehow as the distance to the Noether line. Okay, and M and N, well, we will see later what they are. Okay. So, okay, basically, what's the strategy? We are going to consider a very special configuration of curves in P2. Then we are going to blow up a point. So we will arrive at F1, the Hillsborough surface F1. Then we will apply a Persson's trick. We will get here. And then we will consider a set to square code. Okay. So, and this surface X will be the canonical model of the statement of this theorem. Okay. Now, I hope things won't get very messy because the configuration of curves is not that simple. Okay? Basically, what we need to consider is, first of all, 4 lines in general position. Okay. And let me start to name things. Okay. Let me name these lines. Okay. Okay. Then P1 will be L1 intersection L2. P2 will be L2 intersection L3. P4 will be L1 intersection L4. P5, P3, L1 intersection L3. P5 will be L2 intersection L4. And P6 will be L3 intersection L4. Okay. So we have this point is P1. This point is P2. This point is P3. This point is P4. Okay, then P5, we have it here. And P6 is here. Okay. Now, we have to consider some more lines. Okay. L5 will be the line generated by P1, P6. L6 will be the line generated by P2, P4. Q is L5 intersection L6. L7 is Q, P5. L8 is Q, P3. P7 is L2 intersection L8. Okay, so these are all the elements that we need. So let me draw them. So L5 is P1, P6. So here we have L5. L6 is P2, P4. Okay, so here we have it. This is L6. Okay, L7, I will use blue. You will see why. It is Q. Okay, so this point is Q. And L7 is Q, P5. Okay, so it is this line. And L8 is Q, P3. Q, P3. So it is this line. Okay. And P7 is L2, L8. Okay, so this is the configuration of curves in the projective plane. Okay. Now we blow up. We consider the blow up at Q. And we are going to keep track of some of these lines. Okay. So we consider they blow up at Q. So we started in P2. Now we blow up at Q, and we are in F1. Okay. And we are interested in keeping track of these lines. Okay. So the strict transform of L7, the strict transform of L5, the strict transform of L6, and the strict transform of L8. Okay. And in particular, we will have some singularities on this on these lines. Okay. That they are now fibers of this Hirschsprung surface. Okay, so this is P5, this is P1, P6, P4, P2, P7, P3. Okay, so now we are at F1, and we are going to consider the cyclic cover of Persson streak to amplify the singularities that we have. Okay, in particular, the branch locus will be this fiber L5 and this fiber L6. Okay, so now we apply Persson streak, and we work at F through n plus k. Okay. The fibers that don't belong to the branch locus will be multiplied. Okay, so we will have 2n plus k copies of this fiber L7. Okay. Okay, the same happens for L8. We will have 2n plus k copies. Where we will have the same type of singularities. Okay. And these fibers will not be multiplied because they belong to the branch locus, but the singularities that we have here, they will be amplified. Okay, so here they were transversal, but now because of Persson streak, we will get some tangencies. Okay, that I represent this way. Okay. Okay, so this is P5. P5, this is P6, P1, P2, P4. Okay, and now we are going to consider a set to square cover of this Hirschsprung surface. Okay, so what is the set to square cover that we are going to consider? Well, it will be defined by 3 divisors, as we said before. In particular, we will have B1, that is just the negative section of this Hirschsprung surface. Then we will have B2, that is L4 plus k copies of this fiber. And then we will have B3, that is L1 plus L2 plus L3 plus L5 plus L6 plus L8, 1, L8, M. Okay, so this is the branch locus of the set to square cover that we are going to consider. Okay, and actually we will get a surface with these invariants. Okay, the invariance can be deduced from the theory of abelian covers. Okay, and in particular, from this invariance, we can get the Hodge number H11. It turns out that it is 24n plus 8n plus 15k plus 24. Okay, and now what do we have to do? We just have to count the amount of -2 curves that we get from these singularities. Okay, so actually, from P1, we get two singularities of this type. Okay, from P2, okay, so we are going to get some singularities from these points. Okay, so from P1 we get these singularities. From P2 we get these singularities. From P3 we get these singularities. From P4 we get these singularities. From P5 we get these singularities. And from P7 we get these singularities. Okay, what do we have to do next? We have to sum the sub-indices of these singularities to get the amount of -2 curves in ADA configurations that the minimal resolution of X will have. Okay, so if we sum all these -2 curves, we will get 24n plus 8n plus 15k plus 22. By the way, why do we know that these are the singularities that we get? This follows from the theory of abelian covers together with Persson streak. Okay, so this is quite immediate if you know this theory of abelian covers and Persson streak. Okay, if we count the amount of -2 curves in ADA configurations that we get from resolving these singularities, we see that we get 24n plus 8n plus 15k plus 22. This, I mean, this is not H11 because we have the same thing, but plus 24 instead of 22. The thing is that since we are considering a set-to-square cover of a Hirschsprung surface, we can also consider the pullback of the negative section and the pullback of a fiber. These curves are also numerically independent. And in the end, what we get is that the Picard number of the surface constructed in this way equals this Hodge number H11X. Okay? Sorry, actually, we have to consider the minimal resolution of this set-to-square cover. Okay? And, well, with this claim, the main result follows. Okay? So I think that I can stop here, and if you have any question, I will be glad to answer it.
I believe that there was some questions, no? There were some questions.
Yeah, there are some questions from Javier. He's online, and I don't know whether he can make his questions online or I will produce them.
Okay, as you prefer.
Better if you reproduce them because then the sound will be better, captured.
Okay. Oh,
Hello.
Hello. Yeah.
Hi. I think I was watching the YouTube thing, but I think I was not it was delayed or something because I understand that the talk has finished.
Yeah.
No?
Yeah.
Yeah. Okay. Yeah. I think there was some delay also. In YouTube later. I didn't know the link. So yeah, well, I was well, first thanks Stephen's. Very nice and very well, very interesting and very clear. Yeah, I have some questions. One question is, let me rephrase it in terms of the geography of surfaces with general type. You said it's you are looking for module when the module the surface of the module or there is some surface in the module component of the module which have maximal Picard number. Now I suppose that the examples you make, if you perform well, if you look at the general surfaces of the component, the moduli, the Picard number is is that true, or you know that? The cover.
So how much?
The singularity will be missed. So you won't have.
Yes. Okay. So actually, in general, a lot of different things can happen. So, for instance, if this is not our case, okay, but if we have that PG is equal to 0, okay, then X always have maximal Picard number. Okay, so it actually happens that for some moduli spaces, all surfaces have maximal Picard number. Okay, but this is not our case. Okay, in general, we're only working with this. Okay, but our case. Okay, in general, we're only working with this. Okay, but
Javier, your question is broken, so we cannot listen to you well. Could you please write it up or something, or go to a place with better internet connection, because your sound is broken.
Okay, I think I will say some more things about this, and maybe these other things will answer his question. Okay, so if PG is equal to 0, then X will always have maximal Picard number. So we may have modular spaces such that every point of this modular space has maximal Picard number. Then there are some other weird cases in which and we have some other cases in which there are modular spaces that have connected components without surfaces with maximal Picard number. So these are two extreme cases. We are not working in these two cases, right? So in our case, yes, we will have some surfaces with maximal Picard number, and some other surfaces will not have a maximal Picard number. And actually, indeed, it seems that our examples are pretty exceptional in the modular spaces that we are working with. Why do I say that these examples are pretty exceptional? because as we said when we talked about set2 covers, if we move slightly the branch locus of this set2 square cover, we will get something with less -2 curves. Okay, so in principle, if we move the branch locus, we will get something with less Picard number. Now, what's the Picard number of a general surface in these moduli spaces? I don't really know. It seems that having Picard number 2 could be pretty common, because we will always have the pullback. Well, I mean, if we change if we still consider set2 square covers of this type, and we change the branch locus, we will always have the pullback of the negative section, and we will always have the pullback of a fiber. So it seems that surfaces with Picard number bigger than or equal to 2 should be pretty common. But apart from that, I am not sure what the Picard number of a general surface in these modular spaces should be. I don't know if this helps or not. But
I hope so. I think that he's.
Yeah.
Yeah.
Um,
Try.
It's another. It's
see.
now 1:15, and there's another seminar upcoming at 1:15. I mean, I think that with.
Okay.
If you want another question,
The-
I should
the
go
reason-
back if you want to continue.
You should fix an appointment.
I mean, I have still to prepare everything, so if you have like
Okay,
5 minutes,
yeah.
if you want.
I think that we should invite Vicente for staying here for, I mean, coming to the Complutense for some days, and then you can borrow him for longer. So thanks Vicente again for his wonderful talk.
thank you. Ahora voy.